All right, I think we're competing with the career fair / exhibit hall / trick-or-treating for grown-ups. That's what I did. So we might have more folks wander in. Welcome to the Sweet Fellows Technical Track. We want to call it a technical track. Actually, we've found from audience reaction this morning that folks want more technical content at Sweet conferences, so thank you for sitting in on that. We hope we get more. One of the things we want to proselytize for is in that little program guide summary thing. Instead of calling these presentations educational, it needs to say technical, right? So, and so if that's some feedback that all of us can give is the technical talks need to be identified that way, and then because people have been struggling to find us. So thank you all for finding us, and we'll have an introduction.
Oh, okay.
So we're Virginia.
We're delighted.
Co-chairs. I'm sorry, I should have
That's
mentioned.
okay.
Yeah, co-chair. Virginia has been doing Virginia counts.
Yes.
Has been doing most of the heavy legwork to schedule the sessions. Judy Forbes and I'm Anita Gale, basically conceived this idea of the technical track sponsored by Sweet Fellows 2 years ago. Oh, did I need to say it? I think
that's okay. Why don't you guys, since we are a little bit of a smaller group, would you guys be willing to kind of come up to the front of the church and populate up here so we can kind of have a greater audience? Yay! Thank you guys. So as Anita said, the fellows have a passion to kind of bring back some technical content to the Sweet Conference and make sure that we're able to bring experts here to talk about kind of the latest and greatest in their field so that we can all be up to date. So we are delighted to have Sherry Chen with us today, who's with Keysight Technologies, and I know you've got a big Keysight crew here. Yay, yeah. You also have an award winner, Stacy Chu. Congratulations. So hopefully your brethren will be supporting you in spirit. But Sherry's here to talk to us about a really complicated topic that I'm not even going to attempt to explain to you, because she's going to do that, and she's going to make it simple so that we can all walk away with something that we didn't know before. Does that work?
Yes, thank you. Thank you so much. Hello, everybody. Again, thank you for coming. I know I am between you and dinner, so I'll try to hurry this along. So I am Shari Chen, as she has mentioned, and I am a R&D software engineer at Keysight Technologies. Today, I would like to talk to you about proposing a method to measure error vector magnitude for a generalized frequency division multiplexing signal. So this is, again, my first time attending SWE conference, and I'm really excited to be here. But at the same time, I'm terrified to be up here, so thank you for attending. Okay, so I am proposing a method to determine error vector magnitude, which is called EVM, for a GFDM signal. So what I'm proposing is a synchronization algorithm based on cyclic prefix, which is a CP, denoted by CP, and that will be used to utilize the to gain the time domain synchronization. And then I will use a zero forcing equalization method to do demodulation, and then error vector magnitude results will be compared between a measured signal and ideal reference signal. So this work was part of Keysight Technologies VSA 89600A software solution, which is a standard vector signal analyzer software that we sell. And it's heavily used by a lot of the demodulation companies. And this work was requested by Inatel in Brazil, which is the National Institute of Telecommunications of Brazil. And again, GFDM, which is the Generalized Frequency Division Multiplexing, is still in research phase. It's not been implemented anywhere. So the two major research hubs currently existing is in Brazil and is in Germany. University of Dresden has a lot of PhD students have worked on the GFDM signal and doing some research based on that. So Dr. Luciana Mendes is the key scientist who is heading that GFDM research. So he's the one who requested this, and he's currently working for Inatel in Brazil. So this also doubled up as a thesis project for me at Sonoma State University for my master's in computer engineering science degree. So there are some contents which is probably things that I use for theses, and a lot of math-heavy things I will skip through. And if you're interested in it, I would be glad to share that with you afterwards. And at this moment, I'd like to acknowledge the technical mentorship that was provided for me by Dean Ginger, who's a DSP expert at Keysight Technologies, and also Dr. Brendan Hummel-Bissell, who's my thesis coordinator at Sonoma State University. Okay. So the main application of this software that I'm creating to measure EVM is to qualify a GFDM transmitter pre-distortion corrections. For example, we have a test setup, and we would like to send a transmitter signal without pre-distortion corrections and measure EVM. And we use the same signal with applied pre-distortion corrections and then measure the EVM, and you compare the two to qualify how good of a pre-distortion algorithm that you are using. So, so this is actually, so the EVM results is used for comparison method. So again, as I said, this test setup, it's a collaborative research project being conducted by Dresden University of Technology in Germany and Inatel, which is the National Institute of Telecommunications of Brazil. As I've said, Dr. Luciana Mendes is heading the research, which is, he's the key scientist in GFDM technology currently existing. So this actually shows the test setup by the Inatel and Dresden test setup. As you can see, most of them, all of the equipment that's used are produced by Keysight Technologies. There's a lot of signal sources, spectrum analyzers used in this test setup. Okay, so what is the motivation behind GFDM? So the motivation behind, well, GFDM is one of the technologies proposed for 5G. As we all know, 5G is the next generation of communication. So currently we use OFDM in your cell phones with LTE, and GFDM is another technique that's proposed for 5G. Currently, all of these techniques are in research phase. So we have filter bank multi-carrier FBMC. We also have universal filtered multi-carrier UFM, biorthogonal frequency division multiplexing BFDM, and then we have GFDM, which is the generalized frequency division multiplexing. As I said, the only current implementation, well, all of these methods are in research phase, but we do have a 5G NR implementation currently being tested and used that still uses the OFDM-based technology, which is, it's added a CP-based OFDM technology for 5G new radio, which is called 5G NR. But GFDM is still in research phase, and I have not seen an actual implementation as of yet. So I think this would be beneficial to everybody. Like, I would give a little background of what's frequency division multiplexing, right? So at the beginning, so we had the first generation of our telecommunication was done like with frequency division multiplexing, meaning each subcarrier is divided in the frequency axis. So all of the subcarriers lined up on the frequency axis at different frequencies. And this is what we use for AMS and TACs and NM2, which is very old technology, mostly used for satellite communications. And then came 2G, which is the TDMA technology, which was used in GSM kind of technology that we have used in the previous phones. This uses subcarriers are divided in frequency axis and in time axis. So it's each subcarrier has time and frequency distinction. So then came 3G technology, which uses CDMA. So we use this in the phones with CDMA 2K and WCDMA for 3G. But we didn't have any distinction in the time and frequency axis, but each of the subcarriers had a code associated with it that identified the subcarriers or distinguished subcarriers from each other. So then came 4G, which is current technology that we're using. which is using orthogonal frequency division multiplexing. And again, it has carriers defined in frequency axis and time axis. But there's something special about the frequency axis, which is described in the next image. These frequency subcarriers are divided by delta F frequency, which is which guarantees orthogonality between each subcarrier. So orthogonality means, for example, this red subcarrier's peak lines up exactly with the nulls of the blue and the green and the purple subcarrier. So this means at any given time, only one of the subcarriers is relevant, and all of the other subcarriers would be quiet, so to speak. So that's how we identify each subcarrier, right? So that's why it's very important in this technology that these subcarriers are orthogonal to each other. So what we are proposing is generalized frequency division multiplexing, meaning we generalize this frequency division multiplexing. We're saying we don't need orthogonality between each subcarrier, but you accomplish that by adding each subcarrier goes through a pulse shaping filter up front. So therefore, you don't rely on the actual orthogonality of the subcarriers, but you use a pulse shaping filter to do the subcarrier ID. So for example, if you look at this red, blue, and green signals, you can see they're not orthogonal to each other at all, but they are pulse shaped by a filter up front. So that's a generalization of the orthogonality for GFDM. And there's another difference between OFDM and GFDM. Basically, OFDM, for each subsymbol, this is called a subsymbol. It's separated by a CP, which is a cyclic prefix that we are adding for control purposes, right? So each subsymbol has a CP ahead of it. But in the case of GFDM, we use a block of data and we use one CP up front, and therefore you're not actually wasting your spectrum by using the actual bandwidth to use control information. So we have eliminated the need of a CP for each subcarrier. So again, a generalized frequency division multiplexing, GFDM, generalizes the concept of OFDM. The reason that we want to do this is OFDM notoriously has poor out-of-band performance. It happens due to intercarrier interference, which is also called ICI. What happens is the carriers up front, when you transmit it, you may have a purely orthogonal carriers, but once it goes to the channel with all the Doppler effects and Doppler spread, you have some channel time variations, and that creates carrier frequency offsets, which causes each of the carriers to have crosstalk. So it comes out as crosstalk, and it degraded the performance of the subcarriers. So to avoid that, what OFDM does currently is it adds guard bands and things like that, but this leads to the spectrum being used for anything control or guard bands, CPs. These are all control information that doesn't carry data, right? So it wastes the bandwidth of your spectrum. So what we want to do is minimize the control information and guard bands. Therefore, we use all of the spectrum for data only. So to avoid ICI, so because of the ICI issue, it has poor out-of-band performance. So the highest figure of merit for 5G technology is the spectrum efficiency. So that's why we're doing GFDM, because it actually every symbol passes through a pulse shaping filter, which gives you better out-of-band performance, which gives you spectrum efficiency. And also, as I've shown you earlier, it also goes through, each subsymbol has one cyclic prefix, so that also increases the spectrum efficiency, right? So we're not using the spectrum to add more control information. So this is the GFDM block diagram. This is very similar to any other block diagram for any other technique that I've shown you earlier. So basically at the top you have the transmitter signal that goes through. It starts with the bit rate, a bunch of bit stream that's created, and it goes through some sort of encoding, mapping into a QAM modulation technique. and then it goes through, added all the control information like cyclic prefix, cyclic suffix, and all other guard bands kind of information. So then it goes through the wireless channel, which gets transmitted over, and then it comes to the receiver side of things. So at the receiver, I have to somehow capture the data, time synchronize it to the beginning of the frame, because when you transmit it, usually the receiver has no idea where the beginning of the frame is. So this is why I'm proposing this technique to synchronize, do the time synchronization based on CP. And so what happens is you have to do time synchronization, and then we do removing prefixes, and then we go through some sort of thing called channel equalization, which removes the effects of the channel that's being added while we were transmitting. And then it goes through a demapping sequence, which, because if you transmitted a 64 gram signal, I already know that information, therefore I will try to map it back to a 64 gram constellation. So this highlighted yellow shows the actual blocks that I have implemented using MATLAB runtime DLL. So, so basically this transmitting signal is given to us, and we capture it, and then I use the MATLAB to implement all of these blocks and then retrieve the original data back. So this shows the transmitter side of block diagram, and this shows the receiver side of block diagram, which I will go into details next. Okay, so this is a little math heavy, so I will try to walk through it as best as I can. So, so basically we have a binary source data arranged in k subcarriers with m subsymbols each. So which results in m times k parallel substreams, right? So for example, this blue subsymbol 1, and then the blue highlighted section is subsymbol 2. Each of them has k subcarriers. And then each stream is then upsampled by some known n integer. And then this bit stream is run through a corresponding transmitter filter. And then it goes through, after pulse shaping filter, the baseband transmit signal is, so then, as you can see, so it goes through this Cram signal, each subsymbol gets upsampled, goes through a pulse shaping filter, and then CP and CS are added, and then it gets transmitted. So this transmit filter can be denoted by, if you take GFN as the impulse response of the transmit filter, this is the mathematical equation for the transmit filter. So basically, after pulse shaping filter, the baseband transmit signal in digital domain can be obtained through summation of all subcarriers and subsymbols as shown here with x of n. So basically what you get is, this is a baseband transmit signal. It's a summation of all of the subcarriers with in each subsymbol. So x of n at this point is d of k of m is the data symbol transmitted, and m subsymbol of the kth subcarrier. So when you transmit, this is the baseband transmit signal. When you transfer it to a matrix notation, this is what we actually come up with. So you have the data vector, transmitted vector, x is the matrix notation of the transmitted signal. So basically, at the receiver end, what we are trying to retrieve is the A matrix, which is the one that carries all of the data, original data, right? So I will skip this slide because this talks about the block coding, how we do the circular pulse shaping, and it's a very common technique in DSP. You can look this up if you're interested, or you can come talk to me afterwards. I'll be glad to talk to you about this. So basically what we're doing is we are creating X of AD, but once you add the CP and CS, this transmission matrix changes a little bit. But by using a technique called tail biting and circular pulse shaping, you can actually retrieve the A of transmission matrix A. So now we come to the receiver side of the block diagram. This is the mathematical model of the baseband receiver. So again, we're looking for X of AD. A is the transmitted A is the data that I'm actually looking to retrieve. So as you can see, it's so data has been transmitted through the channel. the first thing I need to do is time synchronize it channel, and then I run it through a CP and CS removal. Once I know the beginning of the frame, I can remove the CP, I can remove the CS, and then I can do some equalization to get rid of all of the channel effects. And then it goes through demapping sequences. Each subsymbol is being retrieved, and then estimated data bits will be received at the end, which is the A matrix. So this is again the math part of it, where H, if you have this is a baseband receiver signal for any wireless channel. Y is equal to H of X convolution of H of X plus V. H is the multipath realization of a channel, and V is the noise vector. So X is the original data that's being transmitted. So I don't know if you have taken any FFT classes. So the convolution in time domain is the multiplication in frequency domain. So in time discrete signal, you get y of n, which is equal to h of n times x of n plus the v of n. So as I've said previously, we're using this as a comparison method for pre-distortion calculations. So since this is not over the AR channel, we can assume that the V of V, which is the AWG and noise vector, is very small. And by using that, then if you take this whole signal and divide it by h of n, so to speak, you find the Fourier transform of y divided by Fourier transform of h signal. And then if you take the inverse of that, you get the equalized signal in frequency domain. So then if you do some matrix manipulation again and try to create a B receiver matrix, you can actually use zero forcing equalization to take the inverse of the A matrix. So at the end, we actually retrieve the A matrix, which has the data. That's the whole purpose. So that's all the math. Let's just forget all of that. Okay, so let's go to, so in real life, how do we do this? So, okay, so I'll give a little bit of description of the frame composition of GFDM, so it's clear when I explain the actual algorithm to you. So for example, we have a GFDM block, which may have m number of subsymbols and k number of subcarriers for each of those subsymbols. And it's prefixed by a cyclic prefix, and then it's ended by a cyclic suffix. And it also goes through a process called windowing, which is like a ramp signal that narrows it down and takes all of the edges off, which it's a much better this is a common technique used in DSP for transmitted signals. So this example shows subsymbol 0, subsymbol 1, subsymbol 2. So in this case, m is equal to 3, and it has 512, k is equal to 512. Each subsymbol has 512 subcarriers. And the CP is 32 symbols long, and CS is 16 samples long in this case. So this actually shows the actual data, what it looks like. So the way we create the CP and CS is actually you take the very end data of a block and you replace it to the front, which creates a CP. So then the very next bit, which is like the, in this case, CS is 4. So next 4 subsamples, I take it and I use it as the very end, which is the cyclical suffix, right? So now we use this information to do the actual time domain synchronization. So I know CP repeats at the beginning, and I know CS repeats right after, and then I have a whole bunch of GFDM data, and again CP repeats at the end of the block, and CS repeats right after that. So once I know this information, then I can use it to get some time domain synchronization, right? Okay, so this is the proposed outline of my algorithm. So first thing we do is we require an IQ record of the signal of sufficient length. For example, if the length of the data record is less than a frame length, I am not able to do any synchronization with it because it's too short. But if in my case, I have requested that the sufficient length is at least 5 frames because it gives me enough time to run it through to figure out the time synchronization. Because in some cases, the first frame could be missed because I only have partial data. So I at least need 3 frames in the middle to get the algorithm to work correctly. So then we also set the right appropriate level to match the source, correct bandwidth, and center frequency. So then we also do a resampling effort to get it up to a certain, in our case with Keysight technologies, we always use 4 times the system sample rate. The reason we do this is in case you have a very small frame with a very small CP, there's only very little samples that you can work with. But if you upsample it by 4, you have 4 times as many data samples to work with, right? So then we use signal correlation, which is the most prevalent pattern recognition technology is used for in GFD, in any frequency division multiplexing. So basically, I use the cyclic prefix as a to cross-correlate with a sliding window to identify the start of a GFDM frame. So basically, cross-correlation, well, I'll explain the cross-correlation next. So then we go into take the CP out of the GFDM frame, take the CS out of the GFDM frame, and then we downsample it by the same sampling rate that I have upsampled prior. And then I do initial demodulation. We use different methods here, like zero forcing, matched filter, or mean square error method to do channel equalization. And then we do measurement demodulation to map the sources crown modulation scheme. And then we construct the ideal subcarrier value based on the modulation format chosen. And then we create ideal signal versus the measured signal and estimate the modulation error. So this is the actual test setup. So we have a GFDM signal generator, which is we use a signal studio software to create a block of GFDM signal. And then we add noise and we add different offsets, and then it gets played by RF signal generator. And this RF signal generator is frequency locked to a spectrum analyzer. So therefore, there's no frequency offsets that we're expecting. So once these two are frequency locked, we use the spectrum analyzer to capture this data, and then we use vector signal analyzer software to take the fast Fourier transforms of this particular particular data stream. So which this provides is a IQ data of the received signal. So then my MATLAB runtime application takes that IQ data and try to go through time synchronization, equalization, demapping to figure out the correct constellation back to the user. So this shows the power spectral density of the typical GFDM signal. As you can see, this is the GFDM symbols, and this is the windowed GFDM signal. Again, this shows the signal studio signal creation, which lets you decide what is the length of the CP, what is the length of the CS, how many subcarriers, how many subsymbols, what type of pulse shaping filter you're using, which roll-off factor, and then different window types. And this is the vector signal analyzer software, which shows you the actual GFDM signal being captured by a FFT spectrum analyzer. So this is the time synchronization portion. So in digital signal processing, cross-correlation is a measure of similarity of two series, right, as a function of displacement of one relative to the other. So mathematically, it is the sliding product of two vectors. It is often used in pattern recognition for two series. So for example, it's very similar to convolution, but it's not the convolution of U of t and V of t. It's actually the cross-correlation is the convolution of complex conjugate of U of t with a tau displacement with a V of t. The reason we use the cross-correlation is to find the pattern recognition, meaning you have two signals, you try to find the lag between the two signals. So if you take a CP of 32, subsymbols 0, 1, and 2 with 512 samples each, and a cyclic suffix of 16, I know how long this frame should be, and I know my CP is repeating at the front and at the back. I know my CS is repeating at right after that and at the very end. So if I take a small chunk of this data stream that is as wide as a CP, and if I cross-correlate it with the larger frame, I should be able to find this point, and I should be able to find this point. Because at those 2 points, you will find the highest autocorrelation peaks, right? Because that's what the cross-correlation does. So this is what it shows. So it shows you at 128, I found a peak, which is the beginning of the CP, beginning of the frame. And I also found a peak at 6400, which is again another CP. So if you calculate the distance between the two, you see it's actually exactly the same length as the frame. So that's how you find the CP. But this is not as easy as it sounds, because a lot of times your CP is very small and there are a lot of noise in the system, so you get false peaks, and there's few other techniques that needs to be done to really find the right frame. Like I said, I used three frames to make sure that I actually found the right frame. And I also used different things like general RMS energy of the whole frame to make sure that I didn't miss anything or I have a lot of noise in that area. So this also, like, then once you find that CP or two peaks, what you do is you divide it by the RMS value of the largest peak, which gives you the beginning, which gives you the highest peak again at cross correlation, and that is the beginning of your actual signal, actual GFDM block. So this shows the MATLAB code I used to implement this algorithm. I think I will skip the zero forcing equalization because again it's kind of boring, and it's a standard technique, so there's MATLAB toolkits that you can do this with. So basically what we're doing is we're trying to eliminate the changes that happen to the signal due to this channel. For example, you have the information coming in, you have a channel effect, and you also have noise. So by taking the inverse of this, inverse FFT of this zero forcing equalization, you are removing reversing the actual channel effects, but it still holds the green part, which is the noise that was added by the channel. So like I said, if you're using over-the-air channel, this is not a very good technique, so we need to do other things like match filter equalization or minimum mean squared error equalization. So version 2 of this software actually has implemented those two methods, which has given much better results for us in the end. But again, this is a standard technique, so if you want to talk about this later or look it up on Google, I'm okay with it. So then the next thing that I do is the root pulse shaping, right? We need to go back to, because the transmitter has sent it through a root raised cosine filter or a raised cosine filter, root cosine filter. So I need to undo those filter effects by taking the FFT shift of the RRC filter implementation. Again, these are all standard techniques for demodulation. So as you can see, with the roll-off factor, the bit error rate gets better as the roll-off factor is smaller, and this is a test data for RC filter and RRC filter. Again, we can talk about this after. Like it's really a mathematical implementation of RRC filter in MATLAB. Okay, so I want to talk a little bit about this one because with the cross correlation, we do get synchronized to the nearest full sample, but there's a possibility that my frame boundary didn't actually line up with the exact whole integer of the subsamples. For example, in here you have a sample index 3 lined up exactly at the frame boundary with this particular sample index at 3. But in this case, my frame boundary is here, but my subsample index 3 is at least a quarter sample off. So these are called subsample synchronization. So what you do is you add a fractional delay filter with Faro structure, which uses a shifting function to shift the full frame by a half a sample, a quarter sample, or eighth of a sample, or 16th of a sample. So by doing so, we can find the best EVM by comparing those results, by moving and shifting the Faro filter. So this actually shows the actual results. So this result was obtained for a 16-gram signal, and it was off by a half a sample. And you see the demodulation was not very good. It has very high EVM. So once I added the Faro structure, you can see it demodulated a lot better than with the subsample synchronization. Okay, So the next thing that happens is the demapping process. So I'll talk a little bit about the error vector magnitude, what it means. The definition of error vector magnitude is that it has an ideal signal and it has a measured signal, and then there's an error between the two. So like this cross is the ideal signal, and this dot is the measured signal, and then there's a difference between the two. So there's a phase error, and then there's a magnitude error. And in this diagram, it shows the red is the crosses, and then all these blue dots are the measured signal. As you can see, they're not lining up exactly, so there's a little bit of error. So for good communications, we want the EVM to be small as possible, right? We want all of the dots to be lined up exactly. So that's why we measure the error vector magnitude. So that gives the indication of how good of a channel that you have up front. So again, we can use the mathematical formula for error vector magnitude is given below. So you have a E of k, which is the difference between the two magnitudes and the phases, and then you divide it by the measured signal, which is the ideal signal reference. So the difference between the two should give you a good error vector magnitude with the RMS value. And also we multiply by 100, so that gives out of a percentage. Okay, so these are the test results. This is the final part of it. So we have, I have created hundreds of test signals and tested it and measured it. But these are the test vectors that actually came from the iNatel actual test setup. So I'm going to give results for these because it means something. It's very representative of what happens in the real life. For example, you can see there are different QAM signals, and there are different number of subsymbols, 3, 5, 7, and then there's number of subcarriers go 64, 128, 256, 512, 1024. So these are all very real signals in real world. So this is the test signal results for what I call ideal data, which means this is the result without any time synchronization. For example, this is just, they have given me, I knew exactly where the boundary was, so I was able to demodulate the signal. So basically, in this block, if you take the time synchronization off, and if they told me this starts at sample 1024, I knew exactly where the boundary was. So then these results just shows the error in my code due to equalization, demodulation, and demapping. And as you can see, the EVM results are very, very good. It's almost nothing, right? So then you go through the whole, you send the whole signal to the full algorithm, which also adds the time synchronization. And as you can see, there's some errors due to time synchronization. But still, all of the results stayed within like less than 1.6 something percent EVM RMS, which is really good for typical results. Again, this shows the ideal results versus the time synchronized results. And this shows the time synchronized results for all 6 vectors. This shows the ideal results for all 6 vectors. And this is the error due to time synchronization algorithm. Again, that all stayed below 2% of EVM RMS percentage, which is really very good for typical wireless channels. And then we also did a test to see how it would hold up with added white Gaussian noise. So for example, you can see as the higher the white Gaussian noise added, the EVM climbs up, which means it's not doing its job very well. So after 30 dB of white Gaussian noise, EVM jumps about 3%, which is not very useful in that case. So this is the actual email I received from Dr. Luciano Mendes, which makes me really happy because he said, this is the first time that a professional equipment is able to measure a full flexible GFDM signal. So yay for Keysight. So actually, so then the future work is again, as I said, there are a lot of reference material written about these things, and I'm giving it in the next slide, which shows you the references. So we have time synchronization accuracy can be increased by adding preambles and adding more control sequences. And another possibility for time synchronization is adding like a training sequences that goes before the actual signal and trains you as a pilot. And then also you can add, better filter equalization, like match filter equalization and minimum mean squared error for equalization, which we have implemented for the second version of this software. These are the references, and any questions? Thank you.